Following lecture will cover sections 14.5 to 14.7. If you recall where we left off with chapter 14, we were looking at the wave number, or where on the x-axis the peak appears, and we were also looking at the intensity of the peak, which has to do with the polarity of the bond that's vibrating. So 14.5 deals with the signal shape. So we have three factors that we're considering: the wave number, the intensity, and the shape. So let's focus on the shape of the peak. And this is pretty straightforward. Some peaks are very broad and some peaks are very narrow. So the broadness of a peak will indicate the presence of certain functional groups. A broad peak is usually due to some form of hydrogen bonding, such as an alcohol that is hydrogen bonding with the lone pair on a neighboring molecule. So these hydrogen bonds are weaker than a regular covalent bond, and the presence of hydrogen bonds stabilizes the very polar uh, covalent bond between the oxygen and the hydrogen. So this is the quote-unquote hydrogen bond, the intermolecular force, and that stabilizes the very polar covalently bonded hydrogen. So if you have a dilute solution, we generally see a narrow peak, but we're basically going to be looking for the presence of a very broad peak indicating the presence of an alcohol or an OH. So for example, um, we can see we have a very broad OH peak here between 3,000 and 3,500. This would be the free OH, and this is the peak that's due to the hydrogen bonding. This is the one we want to focus on, that very broad peak. That indicates the presence of an alcohol. So in problem 14.8, it says the concentration of an alcohol can be selected such that with a broad and narrow signal appearing simultaneously. The broad signal is always at a lower wave number. Explain. Well, that's because this very broad OH peak stabilizes and weakens the bond, therefore shifting it to a lower wave number. Another OH stretch we're going to be looking at is those that result from a carboxylic acid. These are shifted to a little bit lower wave number because remember, carboxylic acids can undergo resonance. Okay, we have an allylic lone pair, and that further stabilizes the molecule. So this OH peak from our carboxylic acid OH is shifted a little bit further to the right as compared to an alcohol OH peak. Also, a diagnostic signal from a carboxylic acid is that carbonyl. It's a very intense peak due to the polarity. That's that C double bond O. And then this broad peak here, that's due to the OH. So, when you see this broad OH and this carbonyl peak, you know you're dealing with a carboxylic acid. If you see a broad OH peak and no carbonyl peak, you're most likely dealing with an alcohol. The hydrogen bonding found in carboxylic acids is often more pronounced because carboxylic acids can form dimers. So it is a very intense, pronounced broad peak, shifted a little bit further to the right as compared to an alcohol. All right, so what I'd like you to do is pause the video and try to identify each of these spectra as a carboxylic acid, an alcohol, or neither. And remember what we're looking for, those broad peaks up around 3,000 to 3,500. When you come back, I'll give you the answers. All right, hopefully you're able to give these a try. Let's take a look at the answers. So in A, we have an alcohol because we have that broad OH peak, but we have no carbonyl. In B, we have neither. We don't see a broad OH peak, and we don't see any intense carbonyl. In C, we have this broad OH peak, and we have that very intense carbonyl, so that's a carboxylic acid. And in D, we have neither. We have the absence of both a broad OH and the absence of a carbonyl peak. Let's take a look at amines and their shape. These functional groups, primary and secondary amines, will give very characteristic signals in the IR spectra. Because the NH bonds can hydrogen bond, we often see a broadened peak for those as well. How do we differentiate between a primary and secondary amine? Well, primary amines will always give two signals, and secondary amines will give one. And we'll talk about exactly why they do that. But remember, a primary amine is a nitrogen connected to a single carbon. A secondary amine is a nitrogen connected to two carbons. The reason that primary amines exhibit two signals is because of we have possible stretching for two different hydrogens. So for a primary amine, in the ballpark of 3,400, 3,400, we're going to see a broadened peak, and there will be two signals. For a secondary amine, we only have one hydrogen stretching possibility, and you're going to see the same general region, but it will be a single peak, a single broad peak, but not quite as broad as an OH peak. So again, the primary amines will show two signals because the NH bonds can vibrate in different ways. We can have symmetric stretching or asymmetric stretching. You don't necessarily have to know the exact types of stretching. However, knowing that a primary amine gives two peaks is the important part here. All right, so now let's put it all together. We've learned several different functional groups and how to identify them. So in this problem, we're going to try to identify each of the spectra as a ketone, an alcohol, a carboxylic acid, a primary amine, or a secondary amine. So pause the video, give these a try in your notes. When you come back, I'll give you the answers. All right, hopefully you're able to give these a try. And let's take a look at each spectrum. Spectra A is a ketone because we've got this very intense carbonyl peak. The carbonyl peak is in the ballpark of 1700-ish, a little bit higher than 1700, and it's very intense. Spectrum B is a carboxylic acid. We've got this broad OH peak, and we have that carbonyl. That's how we know it's a carboxylic acid. Spectra C shows us a secondary amine. We have a broad but not quite as intense peak, and it's a single peak, unlike spectrum D, where we have a broad double peak. That means it's a primary amine, E, we have a ketone. We have our carbonyl, right, around 1700-ish, roughly 1700, and there's no other diagnostic peak, so that tells us it's a ketone. And in spectrum F, this is definitely an alcohol because we have the broad peak around 3400, and there's no carbonyl peak, right, which indicates that it's not a carboxylic acid, but definitely an alcohol. Let's take a look at a couple additional IR examples. Just to give you an idea, there are a few other functional groups that we want to talk about here. However, let's go through these. Alkanes. These basically only have that CH stretch, and below our diagnostic region, so 1500, we don't really care about anything over here, but these are your CH bending. So if it's just an alkane, you're only going to see in our diagnostic region the CH stretch. That's all of these. You have hydrogens, CH, it's all of these. So the most useful bands for an alkane are those around 3000. Alkenes. Now the most useful stretches are going to be your carbon-carbon double bond. That's right here around 16 to 1700. Now we've also seen peaks around 1700 for carbonyls. However, if you notice, this is less intense than a carbonyl. A carbonyl would have a peak with an intensity almost equal to the CH stretch that we see to the left. So we have our diagnostic carbon-carbon double bond, and then we have our diagnostic sp2 hybridized carbon bonded to a hydrogen here. That's CH bond for an sp2 hybridized carbon. If you remember in section earlier in chapter 14, we talked about sp, sp2, and sp3 CH stretches and their relative positions in this region up here. So in summary, alkenes, we're looking for 1, 2 diagnostic peaks. For an alkyne, we have 2 diagnostic peaks, very similar to what we're looking for with alkenes. We have our characteristic carbon-carbon triple bond. This is definitely a little bit further up. Remember, the alkene peak was around 1700. An alkyne, it's going to be a little bit higher, 2100-ish. And then we have our CH stretch for our sp hybridized carbon, and that's even further to the left. It has an even higher wave number than an alkene. The next functional group we're going to look at, which was not a functional group that we focused on earlier in chapter 2, but a nitrile. So a nitrile has the general form of a carbon triple bonded to a nitrogen. So nitriles have diagnostic peaks around 2250, and that indicates the presence of that carbon-nitrogen triple bond. The carbon-carbon triple bond was 2100-ish, so that was sort of here, and the carbon-carbon double bond was around 1700-ish here. So if all you're seeing is a very intense peak around 2200, it's most likely a nitrile. Here's another spectrum of an alcohol. We have our very broad peak around 3,000 to 3,700. And that is sort of the one thing we're looking for an alcohol. There's no other real diagnostic signals for an alcohol in our region above 1,500. Remember, we don't really care about that CO stretch there. We're not looking in the fingerprint region. So we're focused only in our diagnostic region. Aldehydes and ketones. Now, we've already talked about ketones, but we need to talk about aldehydes. For both aldehydes and ketones, we have strong carbonyl signals between 1700 and 1750. So let's take a look at our an aldehyde here and a ketone. So now how do we differentiate an aldehyde from a ketone? With an aldehyde, you're going to see, this is a little bit tricky, your CH bond, that's the aldehydic CH bond right here. That's the diagnostic signal. So that's how that's really what we're looking for to differentiate an aldehyde from a ketone. See, we're missing that set of double peaks there in a ketone. So a ketone has the carbonyl, but it's missing that doublet. And an aldehyde has the intense carbonyl peak, and it's got that doublet there around 2,700. Amines, we've talked about primary and secondary amines. Primary amines have 2 peaks. So this is your primary amine. And your secondary amine just has 1 peak. And it's a broad peak between 32 to 3,600 for both primary and secondary. And remember, we're not concerned with anything in our fingerprint region. Amides. Now, if you can imagine, an amide should have some similarity to an amine. We have the NH stretch. It's a little bit more intense. We have a broad NH stretch. If it's a primary amide, we will have the doublet. And then we also expect to see that carbonyl as well. So an amide can be differentiated from an amine by looking for that carbonyl peak around 1,700-ish. All right, section 14.6 deals with analyzing an IR spectra, going from start to finish, trying to figure out what type of molecule we're working with. So essentially, we're putting it all together here. So let's go through the steps and we'll look at a few examples. Now, the first step is, remember, we want to focus on that diagnostic region. We don't care about anything below 1,500. So you want to first look for double bonds, look for triple bonds, and look for any bonds to hydrogen. And these are the general regions where we're doing that. And then we analyze wave number, intensity, and shape. Now, it gets a little tricky in that 2,700 to 4,000 region here. We've got a lot of stuff going on. The sp3 hybridized carbon hydrogen bonds are down there. We have our sp2, and then our sp. Okay. We have our NH bonds that we're looking for. Those are our amines and amides. And then we have our OHs for our alcohols and our carboxylic acids. Table 14.2 summarizes some of the key signals that are going to help you decide what type of functional groups are present in your molecules. So it's often useful to have this table. You can print this out. I believe it's at the end of the notes when you're solving problems. So let's take a look at one of the problems from the book. This is Skill Builder 14.1. This is embedded in the chapter. We're going to look at a molecule with a molecular formula of C6H10. We're going to analyze its spectra, and we're going to determine the identity of the structure from the following. It's going to be one of these. All right, so let's go through the process. First, we're going to draw our line at 1500. And remember, we don't care about anything to the right. We're going to look for double bonds, triple bonds, and possibly the presence of any CH bonds. So it looks like we've got a possible set of peaks in our double bond region. And remember, the carbonyl peak is very intense, and a carbon-carbon double bond is less intense. So right off the bat, it looks like we could be dealing with something containing a carbonyl and a carbon-carbon double bond. There's definitely no triple bond peaks here. All right, again, we see no carbon-carbon triple bond signals, but we've got our two signals, which indicate a carbon-carbon double bond and a carbon-oxygen double bond. Next, we're going to look for our HX bonds. Now, that's above 3,000. So anything below 3,000 in this region, this whole set of peaks, those are just your sp3 hybridized carbon to hydrogen bonds. And almost every molecule that we're working with will have those. So you're going to see this set of peaks in almost all spectra. They're not very diagnostic. But what is helpful are any peaks to the right. So we're looking for presence of maybe a sp2 hybridized carbon hydrogen, an sp, any amines, or any alcohols or OHs. So if we look at our spectra, we see to the right of 3,000, we do have this one peak, which is indicating the presence of a sp hybridized sp2 hybridized carbon to hydrogen bond. So again, this is reinforcing what we saw previously, where we thought possibly we have a carbon-carbon double bond, and now we're getting support here. All right, it's a carbon-carbon double bond. We're seeing additional evidence of that CH peak. So we know we've got a carbon-carbon double bond. We know we've got a carbon-oxygen bond, and we know we have a vinylic carbon-hydrogen bond. So if we rule out all of the structures that do not contain carbonyls and carbon-carbon double bonds, we get to two possible structures. All right, now let's try to differentiate between the two. To distinguish, let's take a look at our second compound. We know that it's conjugated, and the first is not. Do you see how we have the alternating single and double bonds? That's conjugated. And remember, a conjugated ketone will have a lower wave number than an unconjugated ketone. So our peak did appear at 1720, which indicates that we're dealing with a non-conjugated ketone or an unconjugated ketone. So our deciding factor was exactly where our carbonyl peak was. The fact that it's at 1720 and not 1680 tells us that we're dealing with this structure, that ketone, and not the second. All right. In section 14.7, we're going to look at how we can use IR to distinguish between two compounds, particularly to monitor reaction progress, to help us identify whether our products have been formed and if our reactants have been consumed. By looking for a change in peaks, right, based on some functional group transformation that we're expecting, we can make predictions and draw conclusions about our reaction progress. So, looking for the success of a particular reaction, our first example, let's take a look. So here's our reaction. We want to convert an alcohol into a ketone. So initially, if we're monitoring the reaction early on, we should see the presence of a very broad OH peak. But this should disappear, and hopefully, if the reaction goes to completion, our alcohol peak should go away, and our carbonyl peak around 1700 should be the only diagnostic peak present. So we'd be looking for the disappearance of the OH and the appearance of the carbon-oxygen double bond. And we know where both of those peaks occur. This is roughly 3200, and this would roughly be 1700. For the next example, this was Skill Builder 14.2 from the book. How could IR spectroscopy be used to distinguish the progress of the following reaction? Well, in both of our compounds, we have a carbon-carbon double bond, but we have a CH bond here, and we have a CC bond on everything in the product. So we'd be looking for the disappearance of that sp2 hybridized carbon to hydrogen bond. So I'd say you want to start looking in this double bond region, and we'd see an unsymmetrical CH bond, or we have a symmetrical CH bond. So sometimes symmetrical carbon-carbon bonds disappear. So we have two things going away. As the product forms, the carbon-carbon signal should vanish because symmetrical double bonds are often not detected on IR. So here's your carbon-carbon double bond, and we see that carbon-carbon double bond disappearing. In addition, our carbon to hydrogen, this is your sp2 carbon to hydrogen bond, that disappears. Initially, it should be present. That's our starting material. But the product does not have that carbon-hydrogen bond, so we see that disappearing as well. Section 14.16 deals with the degrees of unsaturation. And this is going to help us to identify what structural features are present in a molecule. So, for example, alkanes are saturated hydrocarbons. They have no unsaturation. So a fully saturated hydrocarbon has the general formula of C to the N, H to the 2N plus 2. A degree of unsaturation would be a pi bond or a ring. So by understanding the degree of unsaturation, we can determine if we have any of the possible structural features. So each degree of unsaturation simply means that the number of hydrogens is reduced by 2. Let's take a look. If we have a fully saturated alkane, C5H12, and we take 2 hydrogens away, CH10, then we have a single degree of unsaturation. If we take 2 more hydrogens away to give us C5H8, then we have 2 degrees of unsaturation. So anything that has a pi bond is considered an unsaturated compound. Let's take a look at a few isomers of C4H6. Now, this molecule has 2 degrees of unsaturation. Now, without knowing that, without knowing how to determine that, let's take a look. So we've got C4H6. Let's look at all the possibilities that this molecule, all of the structural possibilities that we could think of for this molecule. We could have 2 double bonds. You could have 1 triple bond. You could have 2 rings. You could have a ring and a double bond, right? Because we have, remember, for 2 degrees of unsaturation, the formula is C to the N, H to the 2N minus 2 from the previous slide. So each degree of unsaturation means we're either going to have 1 ring or 1 pi bond. So now we're looking for all the combinations, either 2 pi bonds or a pi bond and a ring. And each of these fits the bill. For 2 pi bonds, we could even have 2 rings, or we could have 1 pi bond and 1 ring. So we're going to learn how to calculate the index of hydrogen deficiency, or the HDI. Now, in doing so, we need to first consider what certain groups of certain atoms will do to the HDI. So let's take a look at a halogen. A halogen is treated like a hydrogen atom, so it does not affect the index of hydrogen deficiency. And an oxygen does not affect the index of hydrogen deficiency. A nitrogen increases the number of expected hydrogen atoms by 1, and we can apply the formula here to calculate the index of hydrogen deficiency. And this is going to tell us how many degrees of unsaturation. So in a nutshell, by using this formula, we can determine the number of degrees of unsaturation, which will tell us how many pi bonds or how many rings are present in the molecule. So you're going to need to know this equation and be able to use it. Let's take a look at an example. All right, so Skill Builder 14.4 asks to calculate the HDI given the following formula. So here's our equation, and we're going to plug in the number of carbons, which is 4. We're going to plug in the number of nitrogens, which is 1. We'll plug in the number of hydrogens, which is 8, and the number of halogens. X is halogens, which is 1. So if we plug all of these in to our equation, we calculate an HDI of 1. So that tells us we have 1 degree of unsaturation. And if we recall, a degree of unsaturation can count as a pi bond or a ring. So this molecule must have either one ring or one pi bond. It cannot have a triple bond because a triple bond counts for 2 degrees of unsaturation. So make sure you know how to use this equation. Basically, you're given a molecule, its formula, you're going to plug the values in, calculate the HDI, and understand that it's telling you the degree of unsaturation, and to be able to match up the degree of unsaturation to the presence of either pi bonds or rings.